Hello, so this is Salim Ansari here. I am an intern in CellStrat, and also I have an establishment of my own where I do system solutions, providing for various kind of mobile solutions. But here I am to present to you today the second part of my reinforcement learning lecture, which will basically deal with the two major things, which is model-free reinforcement learning, using two of the algorithms there. One of them is Monte Carlo, and the other one is TD, or temporal differences. So if you look at the screen now, this is basically just
minimizing.
So if you look at the screen now, this is what I'm trying to present. And this would be, and maybe we'll revisit it once more at the end of it to see how it all boils down to this. Now, this is a little complicated and I feel maybe a little dry subject. So I'll try to correlate it with something that we can identify with. And so that is yours.
No, I'm fine.
So basically, when I'm talking about reinforcement learning, I'm talking about how a child develops, the various development stages of a child. If you are able to follow that, then it will give you a good idea of what this type of algorithm is all about. So there are two ways in which, and if you look at it, from the top.
Can you play the PPT actually so that it becomes bigger?
Display mode.
F5. Yeah, but it's already there.
This is Mac, na?
I think different screen is projected. Actually, you have to project the screen, and this
is something else that is
no, you have to do it.
I mean, at least what to expect. That's the main thing. Right. Okay.
You can use marker on board also if needed.
Okay. So this is, can we have the full screen?
Yes, in yours. There's a button here. Huh?
Okay.
Click on this button.
Okay.
I think this one. Yeah.
The third button on the left.
No, see, this is this.
On the left side.
This is this. But it is not happening here.
No, it is happening on your monitor. It has to come here. While sharing, you have to share this screen.
Yeah.
Did it come?
No, something else came.
No, it's
Yeah, that was good.
There are various methods that are involved at various stages of the child's life. Same thing with this specific way of learning. And remember, we are trying to make the computer learn, not to solve a problem, which is very different from what we are doing in software. We have a problem, we have a solution, the guy goes and solves it. Here we are trying to get the computer or the logic to learn from it. So there are three methods that we use. One thing is dynamic programming. When I talk about dynamic programming, that basically means that you have programmed everything for the child. He just has to, when he's born, you give him food, he passes whatever, then you clean him. So it's a very structured way in which its instruction is given. Now you have to go from here to here. So that is the policy where you do dynamic programming, and the policy is available to it with all the aspects. That this is in this state, this is the action you have to take, this is the reward that is going to be there. So this whole policy is very well defined even before the agent has started doing anything. So this is basically what we call as a model. Now, when we go to the next level, this is maybe a child, 1 or 2 years, then you go to the next level where you give the child the freedom to go and explore. So you say, okay, you go and pick up the ball. So once he'll go, twice he'll go, thrice he'll go, and then finally he'll be able to. And then he understands what picking up a ball means. So he has learned that. So where you have And there are a procedure that you tell him. You get up, you walk, so there are steps that you take, and finally you'll get the ball. So that is where Monte Carlo comes in, where the agent is given a start point and an end point. He is given nothing else, no other information. He just has to come and do all these three functions that he takes it a step at a time. In time, there's an action, and then he generates or he sees what the reward is. And then but he has to go through the complete cycle from the start to the end, and in between he has to. So only once he completes the cycle, then it is one iteration. And he doesn't learn in one. He learns in 10,000 of them. After running about 1,000 of it, he gets a good, he's able to get to the end. Because on all the before 1,000 times, he's not able to go to the end at all. Now he goes to the end. The problem is that if the algorithm stops there, then he is not going to learn any more. So what we do is we give him another option. We ask him to move from start to some other direction. That is exploring. So all this time, initially he explores, then he comes up with a policy which is actually working. Then he starts exploring again. You change the condition so that he again goes start. And the final objective of this is to be able to go to the goal and get maximum reward points in the minimum time. So this is what the goal is. And so I'll just go through my presentation here. This is what it requires: experience. So he is basically made to learn from his own experience. So there, the only thing that is happening is he does not require any external data. He's learning it on his own. And each time that he ends the thing, he learns something. Okay, if I have to go from here and there's an obstacle, then I should go from the other. So accordingly, our reward function also changes. When he reaches the end of the cycle or the end of the episode, the rewards get back, and they come in such a way that the total number of rewards that were there while he was going, they get averaged out. He says the experience is divided into episodes, that all episodes have terminated, completion, this thing, and it will be averaged out basically. So in all the episodes, you can terminate on the completion and our value estimated, policy change, and they should be basically averaged out every episode. And so that each time, like Vivek, you're saying, why is the Q value changing such a lot? When we were doing last time we did this Q tables, then the values get changed. So what happens is each time that it gets to the goal, all the reward functions get back propagated, and there is an average that is there, and they get averaged out. So this is how Monte Carlo works.
See, I have a simple analogy on this. So I live my whole life. So when I am, let's say, about to die or dying, then I think, oh, I should have done all these things in all these years. So that is the experience, right? Then God gives me reincarnation. I come, then I come back.
That is one way of looking at it.
Then I come back, then I live the whole life. And again, in the end, I regret. And I say I should have done these things.
I think
so
I would want to be a little more positive.
Okay.
I'm saying that my child, who I have given this thing, he comes back and he knows now how episodes work. So he's in school now.
So parents learn how to control the child.
Yeah. First day the child went, he did not know how to do it.
So we try both praise and punishment.
Yes,
right?
absolutely.
Praise and punishment.
Whatever you learn, it will be helpful in your daughter, not for
Well, see, the reward function is for you to decide. If you are able to decide the correct reward function for your son, he will also do the same thing. If he doesn't get if he doesn't get a pocket money, he won't do it. So just a minute.
The same
So
way
this-
you train the kids by reward and punishment, right?
Reward and punishment is the way that we do it. And then in school, they do it hundreds of times. So now they know that, okay, if I have to go to the school, I come back. At the end of it, what happens? Now there is a concept of, what do you call it? We call it is,
Discount.
no. That's my problem. Just gratification, basically.
Okay.
That is the gratification that you get. Gee, just a minute. I'm very bad with these returns. So this is very much like our returns on investment. So when a child, what is the return on investment? The child learns the knowledge that he gets is the return on investment. So then how do you calculate return on investment? So this is what total return is the equal to the rewards, immediate rewards, plus a discounted form of what to expect in future. Because if you brought him to a school, one thing is he's in school, he's learning ABCD, but the delayed response is that yes, he will get a 10th degree here. So that is how you're calculating. Sometimes you calculate the reward immediately, sometimes you calculate the reward after a certain delay. And each time you do that, that is the philosophy. And then the trajectories is basically the paths that are transferred to go to. And once he's in school, he goes through these episodes. And so what he can do is he can take maybe an episode has 10 classes in a day or 5 classes in a day, and a year is this thing. So that if you want to break up and you say, okay, I want him only to do such and such subjects. So that is also possible. So in Monte Carlo, what you can do is, one thing is you have the history of all the episodes, you have the reward points of all the episodes, but you want to only work on state, say 7 to 10. That is the only states that I want to be. So what you do in the consolidated thing, you go to state 7, figure out what is there, and then it can go in steps.
See, this equation is used for Y-value iteration also, Q-value also, and Monte Carlo also. So what's the difference?
This is basically the only equation that is going to work across all, even for your this one, your dynamic programming also. The only difference that is there is instead of G here, it is a E. E is expected. So in dynamic programming, because it is not done yet, so they say it is expected. The reward for this plus the expected reward for n number of. So that's what we do for simple ideas. Value is mean return. That's what I said. That during the whole episode, all the returns that are there, they get averaged out, and this is the new. So each time that there is a new episode, this guy is improving. So every episode, there is an improvement on the previous policy. Now, if you look at what happens,
like S stands for here?
State. So you have state 0 at the time step 0, time step 1, time step 2. So in our daily life, it could be days, it could be hours, depending on what you want. So this is the state and the action. A is the action and R is the reward. So in that state, what action he takes, what reward he gets, and then what action he takes after that. So this is how the whole cycle works.
So little I can just the state and action. What is action means you're doing something. What is the state?
State is the time moment when you are doing that action. At today you are doing.
In the case of robotics. So what is the state? What is action?
So in time t, the time st, he does an action at. That is, at time s, he does an action a, and he gets a reward r. So that's how this whole thing. So now there are two things. What happens is that if there is a start point and end point, most of the times we have only once you come to the same state. You usually don't go to the same state multiple times, but it may not happen in an episode, in a single episode. Multiple episodes, definitely you'll have. But in the same episode, revisiting the same state usually does not happen. But in case it does, then what we do is we average out the thing and use that only, the one that was the initial. After that, it becomes averaged out. So that is how the Monte Carlo works.
Can you rephrase that last statement?
See, when you have state S0, S1, S2, S3, S4, and usually, even in my example, you'll see there are 10 S10, 10 states are there.
For one particular episode, right?
For one particular episode. Now, but there is an option in which, in one particular episode, the S1 is visited twice.
Okay.
Or S2 is visited. Then the action, what do you do that to that?
How that is possible that once?
Why not? See, you S1, S2, S3, I have to go from here to there.
No, you are saying one state is repeated again.
Yeah, so that's what I'm saying. So the state changes when there has to be another action has taken place, right? So in S1 time, I was there. In S2 time also, I was in the same place. I just got this thing. I just got blocked. I couldn't go. S3 also. So now you are saying 3 AAAs? No, there's only one. So that's how it is. So one thing is that when we reach the point only once, state only once, that is the first time. Repeatedly when you do it, then it gets averaged out, and yeah. So that's what. And now what happens is that there are certain technical things that are there. Basically, there is a concept of bias. So bias, I'm sure people would be aware of. But in our case, if I look at it in the human, is that the child goes from one to the other side. Then at some point of time, he feels that why do I have to do this? He does some shortcut or he does some action which he is not supposed to do if he was doing it for the first time. So similarly, even in algorithm, the algorithm biases because of the repeated number of cycles. So what you do is you reduce the bias. So in Monte Carlo, this is quite possible because there is not really anything that was there previously. It is just the step before or the episode before. So it's not so much. We'll talk about the other parts when bias will come later on. And variance, of course, will be there because it is, I mean, from one episode to the other to the third, there could be variance. By large of law numbers, what they are saying is that if V is the value function, then the expected value for this at gains, what is it?
Reward?
No. Returns. Sorry. So returns are basically if you look at this, the returns is the return at ST is actually the return that you expected at time ST only. So this is how we say, because we are saying NS. NS basically is this. This is number of times that he has approached the same state is NS. And if it comes again, it gets NS plus 1. And then you have increment total returns. Total returns are these. Returns is something that we love in our financial world. So in this case, the returns is basically the knowledge of a child.
This equation, I hope most people understand that.
Are you able to?
Gamma, T plus 1 plus gamma.
See, I think that's my main problem. With all this AI and all this, there's a whole abstraction of mathematics. It is really nothing. You see here, episode I, that is, you just put I as 7, right? So SI is maybe S7, at 7 this thing. 1 is the action. A is the I part of the action. The state is I, the action is A, the reward is R at I. Then our I plus 1. S is state is S plus 1, A action is A plus 1, A I plus 1. I mean, that is just a nomenclature. It has got nothing to do with mathematics. It is the way that is represented. And what it is representing basically is that state and its next state and its next state, and the action corresponding to that states and the reward corresponding to that state. That's all that is. But yes, it looks very daunting, as Vivek says many times. But
So
it is
the
not.
second equation, define G is equal to
The G is the total returns. The total returns is the return on the first RT, that is the RIT, plus the sum of the expected returns. That is basically discount. There is what actually happens in this theorem. Gamma is a fraction of what we say is that the reward that you get now is real, but the reward that you will get in future is unreal, and then there is a element of probability involved. And what is that probability? So what we say is, let us discount that. And so this is known as discount function. Usually it is less than 1. Basically, when it is less than 1 means it will go on reducing. There's a way in which you can decay the whole thing, because in 1 year or 10 years, where will my child be? I don't know. So you say, okay, till maybe 1 year or 2 years, I will take that discounted value of rewards. After that, we'll leave it, let it go. So,
yes, gamma square will discount it.
Yes,
further.
so this is gamma.
Will discount it further.
So this gamma, which is the discount value, is a fraction. And as you see,
So gamma is always less than 1, right? Then
yes.
only it will be always.
No, it is not, or it could be 1 also. If it is 1, basically that means that you are not accounting for your next these things at all.
Discounting the future.
You're not discounting the future at all. Actually, you're discounting the present.
Yeah, now only.
You are just looking at 1. So that part of it is not there. I mean, so usually gamma approaches 0.
But how did this equation come up, like gamma square, gamma, then further t1?
See, it is, I'm not sure what is the main listing for it, but it is basically, they feel that it is almost exponentially that your expected results start decreasing. Whatever you expected, whatever is there. So you discount for those things. And that discount should be something that should be realistic. So it is usually 0.5-ish is what they are saying. But I just want to clarify, this whole, whatever I'm saying here is to introduce you to a concept of reinforcement learning and the details of how it will be done. Actually, when we go to the next step, which is control and which is actually executing this, that is where the implementation part comes in, and that's where we get more details on this.
I have a question about return and reward. What's the difference?
Return is only the immediate thing. Rather, reward is only the immediate action. Return is the collection of rewards, the complete.
Once it reaches the goal.
Yeah.
Once you reach the episode.
No, end of the episode is anyways a reward that you will have. You only get a reward at the end of the episode. Like usually when you end the episode, you get a reward 1. So
smaller, is it return or reward?
Reward. G is the return.
After those episodes, you will get.
How do you get to know the future rewards?
See here, the
future time.
future reward, what they are saying is, see, like I said, defining the reward function is a major thing. In this whole, this thing, there are 2 major things which have been abstracted on this. One thing is the reward function, and the other thing is also the environment. What are the details of the environment? Now, I would want to correlate this similar kind of thing. Remember in physics, we learned atomic structures. So we spent 3 years learning all the protons, neutrons, this, and finally they said, no, nothing of that exists here. There are only clouds. So that's exactly what is this. This is only for your concept. Actually, the problem comes when the data here we have observed, if maybe should have shown it to you before.
No, I give a simple analogy. Like my daughter values immediate toys or gifts most. If I tell her I give you an iPhone after 2 years when you ace the 10th grade, she says, oh, it's okay, not so big deal. So future gratification is discount.
No, I'm not talking about that. I'm talking about this theorem, the way it is going, is
No,
that.
that equation I was saying.
Yeah, the equation is fine.
Rewards are discounted by gamma, and the following year even less. Then I say after 12th I'll give you a cycle. No, that's way too far.
It's kind of
See,
a depreciation.
It's depreciation.
Consideration, right?
No, what I wanted to show you was a little different thing.
That's why gamma square.
See,
gamma
this, I'm just talking about this tabular algorithm. See, this algorithm that we're talking about, this is reinforcement learning with a specific kind of inputs. Now, these kind of inputs are tabular. Same thing as what we had in atomic, this thing where we had protons, neutrons, and everything. They said no. Finally, what is going to happen is we are going to replace this type of data with function approximation. That is, it is going to be, so it is like same thing as you go to the final this thing, class, and once you have done your degree and everything, then they say, okay, now you go to the job. And that's where you see nothing of this is so tabular. It is not so systematic at all. You need to involve a lot of other things. So that is what is going to happen to our even the discussion today. It's more or less a discussion on the basic principles. So please keep it at that. The mathematics part of it is not the ones that are going to actually use, because they are representative, and they will be much more refined once we go to use this in a real life problem, where the inputs are not going to be linear. They are not going to be. They're going to be multiple and more complex. That's where deep learning, deep Q learning, and deep RL networks will come in.
So can we consider gamma as a coefficient in this equation?
Coefficient for
It's a
yeah, it is a coefficient.
Again, it's an assumption, right?
Yes.
It's an assumption. So how do you validate it? Like the value should ideally lies between 0 to 1.
See, it depends again on the final this thing. When you have a reward function and you say, okay, this is the reward that is going to be there. Now, how are you going to divide it, or how are you going to do it, and how do you feel that in future, how is it going to get calculated? That is a different thing as yet. It is like I said.
The property of the environment.
Yes. It's basically a property that we don't know anything about. I mean, it will decay slowly. Like in our case, we have your child goes to school, then college, and in college he has two options. He goes to either science or arts, and then the variables
all the
keep
factors
in.
that we have not considered may come up in the future, or might be
Yes.
change the scenario.
Yes. Like I said, it is more of a conceptual thing as of now. When we go to actual implementation, that's the control part of it. This is the next phase of this is control, where this is the way where you're evaluating a policy, then we are actually implementing a policy. And when we implement the policy, while the policy is being implemented, we go to various stages.
Specific name for this gamma function?
This is discount factor. Discount factor. Okay. So this is what we discussed the first time and the multiple times that we have here. This is the first time and the multiple times that come. Incremental, like I said, there is a possibility of incremental also. You have a data for all the states for multiple episodes, but you're only interested in certain states. That is also possible. It is not like you can, so what you will learn, we'll just go further on. Now, I think last time we had seen a Mars rover. A Mars rover has landed in the space. It is landed in S4 state, and it can go right or left. If it goes, and there is a reward function of 1 here and plus 10 here. So if he has this thing, then how will this theorem actually work? How will Monte Carlo actually work in this? So this 1 to 7 or wherever it ends, after 1 is a termination of the episode, after 7 is also a termination of the episode. After that, it doesn't work.
Yes, we can say that it is landed in the moon.
Yeah, it is landed in the moon.
That is, we can say S1 state. And when he reached the particular.
Yes, now so he can land at any place. He can. We don't know which is the S1. So say if he lands at S4, okay. Now he has to go somewhere. Either it is left or right. So if he goes first the step right, nothing happens. Second step right, nothing happens. So if you look at it, it is like this: 1 0 0 0 0, then plus 10. So it does not. Nothing happens in the S1 thing. S3 से इधर शुरू हुआ, S3, S2, S1. You can go right like this, or you can go like that. So that's what the Land Rover thing can do. Two options: either he can go left or he can go right. Immediate rewards will not be happening in this case. The reward only happens after he reaches. So if he reaches S1, he gets 1. If he reaches S7, he gets 10, and in between there is no reward. So this is this thing of how we can visualize it for this. Does it make sense to?
I think for weather forecast also we can do that.
No, that's fine. I mean, for this specific example, then we get the concept of state, we get the concept of action, we get the concept of reward. So this is how this could pan out. Okay. So if you look at this policy state, so what happens is in this state, this is the action, this is the reward. This state, and then there is 0 here, and this is a termination. So this is the action, this is the reward. So this is, and this when we reach the terminal stage, basically after that we don't go. I mean, we don't move any further. So that's what this thing is, and this is the expectation that this is after the action.
So those who are from electrical or mechanical engineering, is there overlap with control systems?
Yeah.
I mean, I think it is an overlap with life. It's a life science here. Because you compare it with what we are doing in life, it's almost pretty much the same. First, what do you tell the kid? You regiment it. So he 10 times, 20 times you do the same thing. Maths में problem solve करते जाता है. After that it becomes mechanical. कोई भी maths का problem दे दो वो solve कर देता है. Then you give him to this thing, summer school. That becomes his exploration. He explores, goes, gets new knowledge, comes back. He said, yeah, that's fine. So same thing. That agent is getting, one thing is he's getting gratified every moment, and then there's a gratification at the end. Then there is a possibility of moving out of the track. That's all what we are doing in life. So to me, it is more of a life science than of mathematics. And yes, these numbers are there, but like I said, I don't take these numbers seriously, because when we actually go to implement it, the mathematics will be very different. And it will depend on lots of other things. But as a concept, when we're talking about, I feel this is a good way of moving from here. So now the key features, key limitations that they have is there has to be reduces the variance, can capture a lot of data, that's fine. An episode must be there before data, and episode can be used to update the file. So this is an episodic thing. You can't use this formula for a problem where there are no episodes, or where you don't know when the end will come, where it has started from. You are just there in some time, this thing, stamp here, and then you exit somewhere else, and there is nothing that you know. So there's no way that this can be used in non-episodic. It has to be episodic, it has to be related to time and state, and it has to move like that. And it has to.
How many types of policies there?
I'll just choose. This is Monte Carlo policy. The first was this thing, DP, where we programmed the whole thing, dynamically programmed the policy in such a way that the agent knew exactly what he had to do for each state and what are the actions, what are the. There is a possibility that this action may be different. Then we use stochastic probability that, okay, there can be 10 options that he can have. So depending on that, that becomes the responsibility of the DP. That is when you have a model, dynamic program. Then you have the second one, which is Monte Carlo. Third one, which we will come to now, is I feel the amalgamation of the two of them and maybe the ones that could be actually used, because that has both.
So what is advantage over Monte Carlo?
We'll come. I'll show you that. So summarizing, Monte Carlo is this: the estimate when he says the value function for given under this is all the things that we've already discussed. Is there anything that okay, one more thing that is, I think people may not be aware. There is something known as bootstrap. What happens is that you have a problem and you have a context of the problem before you start. There is some information about, say if you are going in the same episode, the child has a way in which he knows that till step 5, till S4, I can do something. After that, I don't know. So there is a concept of bootstrap that comes in here, that you start with some previous knowledge, which is not there here. In Monte Carlo, the concept is not there. Bootstrapping is not there because everything it learns from scratch. It does not have any previous information or knowledge that it can use to solve the problem. So that is there, bootstrapping is there. Converge to a value, a true value. What happens is, what is the convergence mean? When you follow this, then what is the optimal policy that is there? We should always be able to reach the optimal policy. And the optimal policy is basically the minimum states, maximum rewards, and this thing to get to the goal. Now that may happen in thousands, lakhs maybe. But for Monte Carlo, they say that yes, with this, there's a possibility of it happening, mainly because of your discount factor. But that if you do too many iterations, it will somehow converge, or even if it doesn't, to a certain extent, to normal assumptions, it can be reconciled. So the convergence does happen. With Monte Carlo, it can happen. So that's what the advantage of it is, that maybe you may require a lot of work and all that, but if you have. Another thing which is very important is there is the concept of the Marcos state. Here, that state is not really actually used too much because the agent is using the knowledge that he's creating himself. He's not using anyone else's knowledge. So this thing on the world, he's not depending so much on the world. So this is one algorithm that can be used when the state is not Marcos. If it is Marcos, then there is this thing, assumption that we know all the states before it. We'll come to that.
So who will choose the policy? It will be dependent upon that episode, or we will choose particular policy for this particular episode?
See, it depends. I think initially what happens is that you choose a policy, let it work, various ways of which it is known as control. It runs through that. Then, even while execution, you can make some modifications. Maybe on the other cycle, you can make some changes, or you can do some changes and do it on another agent. But initially, the learning is from an existing policy. This assumes that a policy exists. Whether it is good, bad, it doesn't care. Because finally, it is going to be the one who would decide, right? You know the start point, you know the end point. It will use its resources to decide where it wants to go. So that is not a problem. Now, when you want to get specific results, we will talk about it.
Yeah, I want to add an example here. Let's say we are training a new chess player and we want to send them to international competition. So how many times that person has to be trained in chess?
Till he reaches the
thing. So we just say, okay, we'll let that child, that person play chess after 1,000 times, we will hope that he can beat the international grandmaster and deploy him in international competition. So that's how we just decide, okay, after 1,000 tries, whatever the person learned is.
I mean, that is, if you want to say, you want to have an end point. And you feel it's like
benchmarking that.
Yeah.
Now this is the 1,000 is the best.
No, we are just assuming 1,000 attempts are enough to train. If we feel it's less, we will try 5,000 times. So it's just a
yeah, it's a parameter. See, it's what like he says, the benchmark. See, what we can do is there are two ways of stopping it. Either it reaches the benchmark. The chess guy, the chess master XYZ has closed it in whatever score it is there. If you reach that score, you're done. Otherwise, 1,000 episodes is what you get, because you have to stop the things, right?
you have to deploy the algorithm in production.
So then exit has to be decided. And another way of doing it is that the agent falls off. Finish. Then there's nothing to be done. If he falls off from the race, he falls off. That's it. That's another termination. So one thing is based on your benchmark. Second thing is you have episodes or you have conditions which means that. And third thing is the agent collapses or whatever.
Assume it is like a self-driven autonomous car. So you want to train it. So you will train it for India or Palestine, like totally all the states, or like a different condition, like hill station or rainforest condition. So like that, how you.
First, you have to set the parameter.
See, that is the problem. That is where your Marcos environment comes in place. The environment has to be this thing defined, right? What is the environment under which this is going to function? Otherwise, if you don't have that environment done, then there could be a number of. And what is the this thing benchmark for that? And looking at the benchmark, you will come out with a rewards function. That this is how you want to reward. Either the reward is winning. That's a very clear cut thing.
So maybe it'll go in the city road, or it has to go to the highway road, or it has to go to the.
So then they decide the benchmark.
Different
environments and different this thing that it has. This is what you have to achieve. Then only.
It depends on you what benchmark you're going to set on.
So it's a huge problem to be able to define a whole RL problem statement to be able to give in terms of state, in terms of rewards, in terms of returns, and in terms of the environment. What are the parameters that you're actually going to control? Because I mean, we are saying that a robo has to go from here to there, but what if the robo falls because battery has gone down? So that is not done, right? That parameter I didn't have in my. So that is also a very important thing that we have.
One more example is the traveling salesman problem. The salesman has to cover 20 cities in India, but while minimizing the fuel or travel cost. So which city should he? When different cities have different sales potential, which is the reward function. And so, which city should he go first? Should he go Hyderabad first, or Chennai first, or Trivandrum first, and then from there where to go? So, minimizing fuel cost, maximizing sales. Different cities have different sales potential, but the problem is the distance. The fuel cost is it depends on which city. So, how will you, if you think of it, can you solve this problem? Anybody can solve this problem. How do you decide the route of a traveling salesman who has to cover 20 cities and maximize sales while minimizing fuel cost? This problem cannot be solved with any existing algorithm except RL.
So finally, which is the best?
ML and DL cannot solve it. Can MLDL solve this problem? How will you do route planning for this salesman?
Well,
RL is the only technique to do it.
I don't think so.
No,
I don't think so.
Yeah,
I think it's more of a.
Yeah, I cannot do that actually. It can be done.
No, boss, the main thing is to be able to define the problem. What are the benchmarks that you have to follow?
What
is the
is using? That is the question.
no? What is it that you want to achieve?
Deep learning was normal.
So there are older techniques to do that maybe. But in AI world, RL is the way to do it. Yeah. MLDL cannot solve it.
And I feel
best route, that is the best policy.
But again, like, best route depends on a lot of factors.
That's what I'm saying. Best route means what?
What is the best route? Best route
Shortest distance. What about traffic? What about pothole? Could be anything.
The same thing Ola cab is doing and Uber for its cab density. So where to keep the cabs at what time to maximize sales and minimize travel cost of empty cabs?
But that problem statement has to come from them.
I'm saying Ola and Uber also would have to do route planning for their cabs and capacity planning for their cabs accordingly. So they will probably use RM.
Okay, no, maybe that I'll maybe that, but you mentioned RM. Something called now is something called graph neural network. So there's something called graph neural network that is also using route planning.
So possibly there are other things.
Something called new.
That's a new one, na? Graph neural network is a newer one.
Yeah, I know that. So it's like a graph. Even that Google Map implemented with a graph neural network.
But previously, before all this came, optimization problems are solved by linear programming and non-linear programming and dynamic programming.
So some of those aspects have come into our.
I think it's all about how you are able to formulate the problem. If you are able to formulate the problem good enough, I think technology is just one of the things that you can have. But in this case, I mean, yes, RL can definitely do that. And here, I just wanted to make sure that you understood, given this samples of interest and this, we're talking about only a section of the whole episode. States and a number of states within the episode are of interest, then we focus only on that. This, we'll see how we can use it later on. Well, this is the second part, temporal learning. This is the idea of temporal learning.
Another policy.
Yes, and this, see, these are all this is another type of policy, but these are all interrelated. Like you see here, this is a combination of Monte Carlo and dynamic heuristics. How is it there? Like Monte Carlo, TD can learn directly from raw data, which is a very important thing. You don't require any more data without a model for its system. And like DP, it updates estimates based on part of the other learned estimates without waiting for the final. Now there is a difference here. What happens is that in Monte Carlo, we had a start and an end. There was an episode. You could not stop within the episode. The episode had to end before any kind of reward or any kind of returns can be thought of. So in this case, it is very stepwise. And how does this happen is that it is learned. So in DP, there is a concept of what do you call it? Bootstrapping. Bootstrapping means that, okay, like your child, once he's finished his school, then you know it is the reference is that he knows mathematics, English, whatever the subjects are there, he is now ready for the next one. So this part where he's getting ready with all the information that is required to go to the college, that makes him bootstrap ready to go to any other thing. So here also in dynamic programming, because it is a program, so you can run it to a certain level, you can capture the data there, and then use TD to move forward. So now there are two ways of doing it. This is one way where Monte Carlo is there. It doesn't need any information from anywhere. It just goes through. Then there is dynamic program, rather first there is dynamic programming. It says, I don't know anything, you have to tell me everything. And the programmer has to look at all the steps, all the variations, or everything. And he does that and the agent follows it. Then you have Monte Carlo, which has nothing. It says, I will create my own policies and it does it the way it is. But the problem is it is too late. Every time you have to complete the episode, you have to complete so many processes, then it will give you. But there are situations where you don't want all that to be done. You just want a small part of to be done and that's it. So what do you do in that case? You create a bootstrap with the information that equips the agent to go to the next step with whatever information here and be able to get the correct rewards and returns after that. So that is basically TD here. And TD is basically, like you see, they are not different things. They're evolving one to the other to the third. And there is, so in this TD, you have bootstrapping. This is basically what happens here. That is this function that is there, VS, value function with R, and this thing reward with R, and S, and policy is pi, plus gamma times policy with S dash, with the pi, or V dash. Mainly what is happening is it has got the information till V. The next state is V dash. So that in the delta between V and V dash is what this is. So it basically gives the delta between the two, not the total, this thing, total either this one, value function, or even our rewards. It will just give you the reward for that delta. So now you have a way in which you can go piecewise, you can go episodic wise, and you can go completely. So this is the detail that is there. That is, this is the learning rate. The learning rate is very much like the learning rate of our child. How fast he can learn. She can learn. If you can just correlate it to that, that's the way to do it. And returns plus gamma times the returns of the S plus 1, the next state. This is what? Minus the, so this is again the delta that we're talking about. This is how this delta comes in here. Now there is a possibility that there is a TD error because the step size may be different from what is the expected step size. So that is what they are saying, that delta T, that is TD delta T, gamma times value function of S plus 1 time, that is the state, whatever current state, plus 1 times whatever the value function of that, minus the value function of the existing set. Again, it is the delta that we're talking about. So that is one thing that happens in TD a little bit, because there is an error on what is expected, because it has come from bootstrap. So maybe it is different. So that is why it gets abstracted here. Can immediately update the value function, value estimate after these. This is known as tuple, SAR. And S dash is the next state with the same values. S dash, R dash, A dash, A dash, R dash. So once you have completed this, then you go to the tuple. Don't need any episodic settings. There is no episodes that are required. It just goes as per. So here is what you can look at it again in a different way. The same this thing. Pick alpha except first and second reward, and so there is this possibility that we use both of them together. Monte Carlo and this one TD. So what you do is Monte Carlo is you say till step number 10, I use the data that is there. But for the 11th, 12th, 13th step, I want it more approximate, this thing, more accuracy on this, because my episode is 20. I'm only interested in 17, but I want to make some changes in the after state 7. I want to make some changes there. Like if you've gone from here to here, I want to come from here to here, and then maybe I want to go here. So till here I have my route. Now this small step, like when you do in Google Maps, okay, I'm close to this one, Forum Mall. So till Forum Mall it comes. That close to part is the TD part. Okay, that's that delta part where that you can program, that you can use, that information you can use, because till Forum Mall you have all the information how to get there. But from Forum Mall to 3 buildings to the left, right, that is where TD is coming. because only for those focused time that you need them.
So why is that after forum all?
Because see, you have this thing,
So
data.
inside forum all it's tough, but after Google Maps or after this,
No, see, you have data, already data till forum all. Google has all the data, but the location that you are interested in is not there in Google Maps. So then what you do is you use the data till forum from Google Maps, and the delta data that you use TD. So, and because that could be different. It could be left, it could be right, it could be up, it could be down, anywhere. So they say, okay, so this is how I feel that they have been converging.
okay, means the dynamic programming is just like a rule-based program.
Oh, no, it's a program. It's programmed same as any other thing where you are teaching the agent to learn, but you're giving him all the directions on what is the state, at what state, what action is going to be there, on what action, what reward is going to be there, and what is going to be your returns at every point of time. Now, having said this, I think I'm going to say the same thing here for this one. My Mars rover, how does it do it? It does it in steps. It doesn't care what happened previously. It doesn't care what happened. It just Mars rover, this is it. So if for any action of S1, S7 terminates episode. Trajectory is S3, A1, 0, no reward. You're coming from here, S3, A1, 0, there's no reward here, S2, A1. A1 basically means move right or move left. So in this case, A1 is move left. And maybe A2 could be move right. So in this case, you are repeating the same action. So you are repeating the same action in S0, A1, A0, S2, A0, S1, A0, right? And here you're getting 1, S2, A0, and here you're getting a reward 1. This is as per the rover reward function. So this is how this is decided. And you can do the similar thing. If you want reward 10, then you will have to say that S4, A1, 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 10. Right? The first visit MC of this thing for each visit is this. And if you look at it in terms of the functionality and the states, then this is the action. It is only one step, and then it reaches here. It does not wait for any other thing. There are no other options that you get. There's only one step that it takes. Guys, any questions from you all?
Anything from ISRO should ask you.
Because of rover?
Yeah, rover.
But that is not my this thing at all. I don't even know whether it exists. So now,
But then even what you're talking about, the models, something from aerospace or people who are building robots.
not really.
No, I think these can be implemented to any problems. Like
We are amplifying them too much. These are ordinary problems. Only thing is that because it's a new thing and because we have not gone into detail, the main thing with this is I feel reinforcement learning is the first step to abstract mathematics from artificial intelligence. Because yes, mathematics is required, but the whole set of other things that are required for the problem to be actually solved is much more. And we get involved in the mathematics of it too much to actually look at it as a solution. Because then we are solving our algorithm problems like this. Especially we in India with maths, this thing is huge. I mean, there is no way, the way that he was able to solve that equation, I was amazed. Some third degree or fourth degree equation, he was able to solve it in 2 minutes, not even 2 minutes. So that is there. That is huge. Yeah, I mean, there he's our But the thing is that there is more to it than that for IIT. I'm sure this is just the beginning, just a representation of that. But we should be very clear about it. We should not get, I mean, I think you asked a question, right? Is maths really required? Not really. If you are not averse to maths, looking at these symbols, pi, tile, you get a little this thing. But that's about all. Because a lot of mathematics is already solved in the algorithms that you will be using as a API. A lot more has to be done to make the solution there. I mean, the data pre-processing, the post-processing.
So you don't have to do maths. You have to understand what does that mean and what is it.
How can you use it?
How can you use it?
And that is also very limited because there are only few entry points to that, which are known as hyperparameters. You only have this thing of playing around with the hyperparameters, but yes, you need to know the details of it. What is it that it actually does? How it does it is not really everybody's cup of tea.
So you want to develop your own model, then only you need method, or you want to use the existing model, the existing API, then no need of models.
See, it's like this. You want to have a fleet of cars, right? That is where the money is. You have 10 cars, you sell it out. You don't need to know the engine of it. Right? Why do you need to know the engine? Yeah, it could be anything. Unless you want to be sell the engine, that's it.
Do you want to become Elon Musk?
Well, I mean, that is all.
Now,
उसका भी कुछ नहीं आता वो सिर्फ बात करते हैं वो Elon Musk.
So you want to be like a nurse, or you want to be like a doctor? Doctor has to know everything. Nurse has to give the tablet for a fever to give this tablet.
Yeah. So this is the next part where we have to say, so okay, these are algorithms that are there. Now, how do we evaluate this? The whole presentation was how to evaluate your various policies. So there are multiple ways in which you can compare the policies. So one way is by properties based on bias and variance, because bias and variance make a lot of difference when we are actually looking at a solution, because then the robo has to go in a straight line, he goes in circles because of the straight line just gets cut in 2-3 places and he does 10,000 episodes on that. So his trajectory will change. So it is very essential for the bias to be corrected multiple times and to understand how to correct it for a specific kind of algorithm. And same with variance. And then data efficiency. I mean, how much data is required for this kind of algorithm? Like we were talking, I think, that I feel that data, the importance of data is hugely overrated as of now. Yes, it is used now, but with these kind of technologies coming in, a lot of it will get abstracted, and the technology will develop its own data on its real time and move forward, rather than creating a model based on a specific old time data. So that's pretty much what is there. Now let me just go one by one. See, usable when no model is of the current domain, right? So which one can have if there is no model? So we already know that it is this one, Monte Carlo and TD. Then a handle continuous non-episodic domains. Again, Monte Carlo is the one which requires episodes, the rest of the two don't. Handles non-Markovian domains. Now, one thing that when we are talking about this one, bootstrapping, the information in that bootstrap has to be total, such that it can make the agent go to the next state. If there is anything in terms of the information which is not available to the agent, then the agent may not be able to move forward. But where do we need bootstrap basically? We are saying we need bootstrap for DP. This thing, what is it? It is dynamic planning. So, and also TD, because there is a bootstrap that is required and we need to have information. The bootstrap basically means that all information that is required, that means it has to be part of a Markovian environment. Because Markovian environment, by definition, is something that encompasses all the properties of use to the agent. Then only you can say that yes, these algorithms can be applied. Having said that, it is not that you can't apply. It is only that what the goal for any application is that it has to have a convergence somewhere. It has to be optimal. Those kind of properties may not be able to be attained if the environment is not Markov. Otherwise, it works. I mean, it's like, okay, will this, if I study maths, will I not be eligible for engineering? No, I mean, it's not like that. Yeah, you can have maths, and that is, I mean, in case of maths and engineering, yes, but say social sciences or some other extra thing, yes and no both. But you will be useful if you have physics, chemistry, this. So this is how Markovian this thing also, policy is also the same. That yes, you have this. If you have everything, then you have a clear-cut goal that yes, you can converge or not converge. You have controlled environment. If the control is not there, then there can be variations. And then convergence to true value in a limit, DP, yes, because there is a program, specific program written for the whole problem, so it has to converge. For MC, yes, you can do it, like I said, multiple times if you do the same thing over and over again. There is an optimal way in which it can go to optimal policy. That can happen. And TD also, yes, because it depends on how you define your bootstrap. If it is possible to get to the next level, yes, you can do that. Convergence is possible in all. An unbiased estimate of the value, well, in DP, because you have programmed it, so everything is in your control. It doesn't matter, so definitely it is going to be there. Markov, this one, Monte Carlo, yes, we have said that, okay, it is every time it is episode to episode, episode to episode. There's very little variance in that. But in case of TD, where you are bootstrapping or when you are trying to start from even zero, next step to third, second step to third step, there can be variance and bias. So this is how this whole thing can be sorted out. And then you have, based on bias and variance, we have this. You can go through it and see if there's anything. Anything that you have here which requires any explanation. So going into comparative data, again, the same thing, data computation in this thing, our MC, data will get accumulated because to come to a place where you have to have an optimal policy, it will require a lot of cycles going and coming. In terms of this one, TD, well, not much, because what you can do is you can take one step, and once you have reached that step, you may not require the previous data at all. So you can delete all the data. So the data requirement for TD is very less. It will depend if you want to do it, but on a problem statement, TD is the minimum. Then you have, in the simplest TD, you use this once updated, the operation is done. But in the second episode, it becomes zero because there is no requirement of the previous one. There is no backtrack. There is no validation on that. And you can be more efficient in simple TD. TD is twice if Markov domain leverages. Again, TD is exploiting Markov because it is using the this one, your bootstrapping, and once it uses that, then it becomes that much easier for it to. And the same example, the Mars rover, you have this. So if it is 1, any action for S1 and S7 terminates the episode. This is the basis of it. Trajectory is S3, S2. The same, A1 is on here, right? So this is the first MC estimation is this. First, is there anything that is there here which you would want us to? Because we have gone through it more and more number of times.
So trajectories can be lot more than just one.
Yeah, multiple trajectories. There can be multiple. There could be only one optimal trajectory, but there are multiple trajectories otherwise. And what happens is once the trajectory is identified, then there is a probability. What we do is we give the agent an option of exploring. He does not take this thing of the best option in terms of the trajectory, the policy. The policy gives them an option of taking another track. Just change one and take another. So there is both exploitation and exploration, both available in Monte Carlo.
For every episode, there will be one trajectory.
Yes, for every episode. No. For every episode, there will be one trajectory, and for there could be a successful trajectory also, multiple successful trajectories, because trajectory could be anything. But finally, the one that actually covers everything. And sometimes what happens is it does not go from end to end. Sometimes it breaks, and so those kind of things we go to once we are in the control part, where we are actually looking at it and see. But as far as the concept is concerned, this is how it goes. And like I said, there is a possibility of TD and MC being used together. We used MC till one extent and then used TD to take a detour.
Easy to maintain trade-off between bias.
Yes, very easy, and then it will be much easier for you to. So here's an example. Let us see if.
Yes, Salim, can you speak louder? I know you may be tired, but.
Okay, is it? I mean, are people not able to hear?
No, for the webinar folks.
Okay. Oh, I didn't realize that. Okay, there are two states, A and B, and gamma is 1. Given 8 episodes, there are 8 episodes. A is 0, B is 0 to start with. Then B is 1, 8 times, and B is 0. So there is 2 times B is 0, 6 times B is 1. So what is it that is there? What is V by A? V by A basically is value function of A when given B. So here, if you look at it, 2 states A and B are there, given this. So what there, I'll give you the working of it actually. Using Monte Carlo process, we get Vs is equal to 6 by 8, right? Monte Carlo, you have episodes. So there are 6, in 6 episodes, B is 1 out of 8. So this is V by 4 is 8. For A, there is only 1, basically. If you look at it, VA is 3 by 4 and VB is, there's actually 1 only. VS we get A to B आया, B to 1 आ सकता है, 2 आ सकता है. So if we are VB has 2 times 6 times 1, 2 times 0. So this is B. VA has only one, it is not going anywhere, it is only one distance, so basically it is 0. And if it is TD, if we put in the same formula, is only one step this guy is taking. This is also 3 by 4. Same, 6 by 8, because it is, there's only one step. In this case, there's only one step, so both of them are the same. And VA is.
We have multiple steps and we have multiple episodes.
Oh, yes, you can have multiple steps and multiple episodes means. In what way are you?
So your observed values and
Which observed?
for example, you have A to B.
This is just one specific from A to B, and then this thing is problem statement is this. The problem statement is this. Now you can have multiple steps, definitely. This was just to give us an idea, okay, this is how it will look. But yes, you will have multiple steps, you will have multiple options that are going to be there. Like I said, once the trajectory comes into from start to end, once that trajectory is covered, then the agent gets an option of exploring. It explores the next route. It explores the third trajectories. So finally, once all the thing is done, that's why we are talking about not thousands, lakhs of cycles to happen, and then get the optimal one. So yes, there is a probability that this can happen in Monte Carlo. It can happen, but in this one, TD, it happens all the time. So. Yes, guys. Anything? Any other questions you have? Anything?
When we implement it, is there a hyperparameter like how many steps maximum I can
Oh
take?
yes, actually, when we are implementing it, there are many more options that are available. I wouldn't want to go into it because it's a different ball game altogether. We will do it next time maybe, because what happens is while you are implementing it, you can change the policy on the fly also, and you can change the policy at the end of. But after every episode, yes, but within episodes you can change. Then you have other out of policy. You have a trajectory of 20 available. Then after that you can do. So those kind of things we'll do a little later because there are multiple complexities that come in. Like one major problem would be, yes, we have a policy, but this guy does not take the complete trajectory. It just stops somewhere. What happens? Whether the next step will be from there or from the start or from. So there are multiple things that we can talk about. But as of now, this is only about evaluating the policy. A policy basically a valid policy is there. It may not be the correct one, but the policy is valid, and we evaluated it. And the two ways of evaluation were, one was Monte Carlo, the other one was TD, and we were trying to kind of bundle together the whole thing to see whether. So that's it. Vivek, anything else that you would want? Hello. Good afternoon or evening, as the time may be. This is Salim back here. Now, whatever we had done as a theory for our reinforcement learning with TD and Monte Carlo, there is a small code demo that I just want to run with you. This is basically a code on how blackjack cards game is solved using Monte Carlo. So the way that it is done, it is on Colab, in Google Colab, and we have used the class blackjack solutions for this, which gives us functions to set up all the players, the game, the players. If you see here, the Q values for the players are there, the range between 12 and 22. Do I have to go through the blackjack this thing also? The game, how is it played?
Yeah, I don't think in India people play blackjack that much.
Okay, so even I'm a little new to blackjack, so I may not be able to give you everything. I'm sure people here would be more. So here, this is a cards game, which is played by multiple people, I guess. And you are served 3 cards at a time.
Against the casino you play. Right?
Yeah, we play it against the casino, and the casino has 2 cards.
No, one. They give one by one. I mean,
One by the casino has some cards open.
only one.
They have 1 card open, and the trick is to be able to go to the magic number of 21, right? With whatever cards that you get. So basically, the challenge for the player is to be able to ask for 1 or 2 cards or multiple cards, such that his overall number should be 21. If it exceeds 21, then he loses. And if the dealer is able to, I mean, I'm not sure how that.
Whoever reaches closest to 21, but below 21 or below wins.
So and what about the dealer?
No, dealer is also competing.
First,
So
the player plays, he can open as many cards he wants.
as many, okay.
Yeah, and then once he can, till he goes till 21. Before 21, like let's say I get 19, I can say stop. Now, if you're the dealer, you're supposed to beat. You have to get 19 to tie, 20 to win, or 21 to win. If you get above 21, you automatically lose.
Okay. So I guess.
I'm opening my cards. If I get above 21, I automatically lose before even the dealer.
You count the cards like 3 plus 4 plus all
the colored cards are actually, I think, 10.
10.
All of them are 10. Ace is either 1 or 11.
Correct.
Depending on how you want to use it. And the rest of the numbers are basically whatever is the number of the card. So if you look at this first part, this is where we are setting up things. This is blackjack solutions framework that we are using, and we are calling the various Q values for IJK. I think IJK value is right. So basically we have ace with two different groups. One is when you want the ace to be 11, and the other one is when we want the ace to be 1. And then you have the action basically is I is equal to if I is 21 and A is 0, then they give a value of Q value or IJK is equal to 1, else the value is 0. So from what I understand, either he hits or he stands, or what is the other. So if it is a 1, that means he is hit, and if it is a 0, that means he is not playing, right? He has lost, or he's
has withdrawn.
Withdrawn, right?
So 1 means give me 1 more card, right?
So I have this code here. I would run it in steps.
We are not using any library, right? We're writing everything.
I think everything is written.
What is it?
Pickle, I think.
Storing the money. Yeah.
If you want to store, if you want to save it.
No, you use pickle. That's why it's for
Yeah.
serialization.
Okay.
You can use it to compress data also, but in this case, I think that is not.
Pickle is like Java serializer.
Yes.
You can store it on hard disk.
Unfortunately, I'm not complete owner of this code, so there could be some things which I may not be able to answer. But my intention was basically to run the code and see what are how it works. But like my theory sessions, it is basically a representative of what we are trying to achieve. So this whole function that we saw here is basically setting up the game with the numbers, and starting here, we start playing. And round 0, in it 13 and 10, and false is basically not 1.
So here 1 player is playing, or
1 player and 1 dealer.
Okay, only 1 player.
One player, 1 dealer. So there is one this thing, winner test, that is there. They have played their cards. Now you run the things, and this is the probability of how this works. P value and D value. This is player value and the dealer value. And the third, this thing is the reward. So player, dealer is 26. 1 is the reward. Then 24 is the player value. Dealer again is 16. Then the reward is -1. And 15 is there in the next hand. And we have 0 reward. Then basically anything that is not a hit is a -1, and I think every time that he he passes, it's a 0. 1 is when he wins, and So this is how this thing works here. They are playing for the first round.
So left side value, that's the player, and
Left side.
The first two columns.
First two columns.
1 minus 1 0. I didn't understand.
One, I think it is stop. I mean, they have not. He's not taken it.
Same. So it's 0. Nobody wins.
0 is draw. Draw.
Draw. There's no one is there. -1 is when he loses. +1 is when he wins. So these are the numbers that are there, and
so
he's.
1 is when player loses. -1 is when.
No, this is -1 is player loses. Player loses. 1 is when player wins. Now in the dealer test, it will be the opposite.
Right.
So this dealer is losing all the time except for 2020 that it has won. So 18 is also he's won. So this is a game that is played mainly. What I would want to emphasize here is this. What do you call it? Just a minute. This blackjack solution, that itself is basically the Markov environment. So everything that the player needs to know about this game is available to it, and it is initialized at this point of time. So this is what the main thing that we can say from. So we have all the these things here, all the variables and their values here, all the parameters here. So this becomes a Markov environment, and then we run it, and this is basically an example of a Markov environment playing this game. So when
if somebody wants to use this code to play the game, then I'll be the player and dealer will be computer, or how is it?
Dealer will be the computer.
So the question is now logically that as we keep on training, the dealer should be more expert in playing, right?
The dealer should be, yes. See, the objective of this game is to create.
When we see that playing 1,000 times or 100 times.
See, I have tried to do it 10,000 times.
I don't see how the dealer is getting trained and become more proficient.
I think this is a simulation.
Yeah, it's all the same.
Play 10 times also. First, dealer will always lose, but starts winning.
Yeah, so we have played this. Wait. So this was only.
This looks more random now.
At the moment, now let us play it for 10,000 times.
Or maybe 100 times. Let's take 10,000 now.
Just a minute. Just a minute.
The second question is that we have always seen RL being implemented on a gaming scenario.
Because of the Markov environment. Because it is much simpler to do it. See, like I said, whatever we are doing for tabular data. In the real world, there is no tabular data. It is like same thing as our atomic theory, right? There is nothing like a neutron, proton, and everything. They are clouds that we're talking about. So when we go to functional approximation, then we actually get to see the real. This is just a demonstrative thing. So that's why wherever they are saying games and the robos, this is all because they want this Markov thing to be there, and that becomes easier. As things get more complicated,
low hanging fruit.
Very low.
But robotics, driverless car, financial services, so many areas.
No, because there is a defined parameters.
The route planning, it can help. Let's say I have to reach from here to Marthahalli. What is the best route? So I can do that.
I don't think even Ola or Uber are using any RL techniques for.
They already have data from Google.
But we don't know. We don't know.
But some optimization they'll definitely.
They have big AI teams. See how many cars are needed in Belantur at this point and which location. Yes. So I think how will you do that?
You see, the only thing is if we have the details of all the variables that are required, then it becomes a Markov. You can create it in a Markov thing. But if there are parameters that are beyond your control or which cannot be available, then it becomes difficult.
Defining the environment in RL is very complicated.
Yes. defining the environment, defining the reward function. One of the most difficult things is to how do you define a reward function for it to be able to do what you wanted it to do. And here the purpose of this blackjack test is basically to kind of identify the benchmark in blackjack for the casinos so that they can go back and say, okay, whoever plays, the players, they will grade as per their benchmark. So with these kind of simulated environments, they're trying to solve it. I don't know whether they're able to actually get the right result, but and the dealer will be, the ideal dealer would be the one who is able to get to the back to win the maximum number of matches and in the minimum steps possible. So if that happens, then that becomes a benchmark. That if, and from there you see, okay, whatever point system that they have. So, okay, I ran the program and here we have this with when we have, I think, 399 as wins by the dealer, 1835 as losers, and 412 as draws.
So now I want to play these games, I can play with this dealer?
Yeah. But at the moment, I think both the player and this thing are simulated. We are not doing it as per this.
If you run it 100 times, now you got the ratio of this.
Yeah, yeah.
If you run 100 times, is the percentage, why is the win ratio of the player is more or less?
We'll just play it.
I mean, get the numbers actually right now. What's the number? Yeah. What's the percentage?
Change the iteration.
Numbers change iteration. Then we'll know that the agent will be able to learn.
See here, I showed you the numbers.
You reduce 1 0 then
1 0 you did, then see that what is the percentage?
See this array that you have 403 1821. Now I am running it for another.
So who's winning how much?
This is B player with dealer 1000 times, and this is what the.
4003. Who's winning 4003? Dealer or player?
That's the dealer.
Dealer.
Now I run it another 10,000 times. Let's see what happens. Now it's 4064 1710 4226.
If you reduce the round to say 5,000, then the percentage.
Okay.
So now it is 40%.
Is it 40%?
Yes.
5,000, and then we run it again. So now it is 2. Okay.
So it will learn. It is learning earlier than 5,000 also. You make it 1,000, then it is enough.
Now let us put it as 500 and see what happens. 205.
So 205 is a dealer.
Yeah.
So the percentage is not changing.
When we run this is already setting the
Play with the same strategy.
Then how is the learning actually?
Then we have to run from the beginning.
Let's go.
Reset the policy. Even the percentage should have changed.
Policy reset basically means I'm thinking that it is saving.
You ran the model on
Each
top.
Run from the beginning, the policy values will.
I mean, you ran the model on top of the earlier run.
Yes, you're right.
So the percentage of win of the dealer, not the dealer should increase. Should have increased.
Should have increased, yes.
So now total EPO is 10,000 plus 5,000.
So now, but I have run it multiple times even before. So I don't know whether it is storing it or not.
It's not learning then.
And it is not storing it.
From the beginning, everything will overwritten.
Okay, let us see.
You can run it from beginning, but
Okay.
you just run it again, rerun it.
We will do that.
Total EPO is 15,000 it has run.
We'll just rerun the whole thing, don't worry. We'll reset and rerun. Run before, after. Run all.
and run all.
Restart कर दिया था पहले. Oh wait, let's.
40%, it is becoming 10.
Exactly. Now, actually, you should go
190.
Then only they'll make money. Otherwise, they'll
So
not
it
make
is
money.
50%.
They lose money.
Now it is 50%, right?
How many EPOs?
500.
So 500 EPO,
No, it's
50%.
not 50%. It's less than 40% now. 190, right?
Slightly less than. Earlier it was 204 for
Yeah,
500.
190.
You go to the previous sir.
It has learned little bit.
10,000.
If you increase the
No,
EPO,
that is for a different strategy. What we'll do is we'll reset everything. Hmm. Hmm.
restart.
Restart.
Yes, yeah.
Okay. I need to put the charger on. Where is my bag? Okay.
It's just demonstrating the RL process.
Yeah.
It's not actually training either of them.
Correct.
See, this I am not also putting too much emphasis here because this is a theory session, and unless we do control, that is when we are executing it, then we have much better idea of what is happening. Here it is just a given policy which is running, and you don't even know what the policy is. So I think that we shouldn't put too much emphasis on what we are getting. Yeah. Hmm? What is this? What is it? Because it is running 10,000 episodes. Here.
Let's go outside the box. Outside. Ah.
So here it is 216, 70, 214. It's pretty much 50%.
Better than last.
So like I said, this was a representative code, not too much there in terms of creating or as they call it, control runs. It's not done. But this was just how the code here is written and how we look at this as a Markov environment.
So I have one question for you.
Sure, please.
So classic ML, vision, NLP, RL. So what is your curiosity about RL? Sort of an offline question.
Yeah, I feel that RL is the future because, like I said, I have my very strong these things about how far this data
most
thing.
People in our interns in our AI lab pick up, let's say, vision or NLP, or some do classic ML. Not many people pick RL as an area of focus. So what piqued your interest in RL?
I feel that I had read about RL a little bit, but when I went into the depth of it, I found that it is so close to what I see on a daily basis that I was able to identify with the processes and the flow of this much more than just the mathematics.
Have you had a chance to look at the book by Dr. Rick Sutton?
Yes. I am actually, I would refer a lot of it.
Or you refer to. That's a very difficult book to understand.
Yeah, it's a difficult one, but you do it in bits and pieces and it works.
You have to kind of read it again.
Yes, yes. And for this also, to be able to understand where it is all going.
I bought that book about 2 months back, the new version. I'm still on chapter 1.
Yeah, I just keep doing it as for what I want.
I'm not able to get to chapter 2.
What I usually do is I go to the presentations and all, look at whatever is there, content, and then to go to the depth, I go to that book.
Okay.
To figure out, okay, this is the details of it. Because usually in those presentations and those classes, it's just the tip of the iceberg. So yes, this is something that
There's
I would
also one course by David Silver, I believe, very famous on RL. You came across that course?
Oh yes, I have taken that reference also.
David Silver,
and that lady also, Emma.
Okay.
Emma also, two of them were the major things, plus the book that you mentioned.
Right.
Both of all these three were the
I think Giron has a very good RL chapter. Aurelian Giron, the last
Okay.
chapter is on RL. It's quite understandable. It is quite good.
To me, like I said, I didn't find understanding RL that challenging, because I was able to identify it, and the math that you said, math is mainly representative till now. I still need to go into the execution phase to understand how much of it is actually math, because I personally feel that RL is an abstraction of math to the AI, because AI people want to create solutions.
Like also similar to behavioral psychology. So
Yes.
psychologists may use behavioral techniques to condition human behavior, right?
And I think that's where this thing is there. No? The references, AI is there because they're saying that they are trying to replicate our neural networks. And I feel, so when I look at it from that angle, I feel it is much easier for me to identify. Yes, maybe the mathematics could be difficult. And like I said, the proof of the pudding and the devil is in the details. But the details that I feel will be more involved is how we define the reward functions, how we define the environment of that, and what is it that we are actually going to call Markov framework or Markov compliance, as they say. If these things are there. And also, of course, this is all tabular. Once we go to the real world, everything will be functional. Then things like your stock exchange and more involved problems, they would be having a lot of, because convergence and optimal theory and all that will become more and more.
So any questions, final question from audience? Yes.
Yeah. Sorry, I didn't have a chance to look at your background, but could you talk about some examples, real world examples where you used RL and how did you go about it?
See, one thing is that I have not gone that far. I am just a student of RL and trying to, but like I said, it is mainly at the moment from what I am seeing in RL is mainly dependent on where we are able to control our environment as much as possible. So like he says, gaming is one of them, because it's one thing, it is not a serious thing. So even if things don't work out, there are no major failures. So that is another thing. But the other problem on where it can be used, I feel there's a lot. My theory, my thought is that we have come some way in ML, increased our depth and capability with DL, neural networks. Now these neural networks have solved the problem to a certain extent. There would be, the future of this is DL. Because like today I was talking to someone, one of our, who was actually using AI, and he says the main problem is that people are looking at accuracies of more than 98% or 100% in this. And for that, we need to train data multiple times. So that training of data may be overcome by using RL. That it uses the data that it gets and trains itself. Rather than, so I think this could be a logical progression. You have ML solution which solves part of the problem. It goes deeper, we go to DL. And then when it is actually on the field and the new data is coming in and you don't have, then RL. That's what I feel. It's basically just a gut feel. I don't have any things to, yeah. No. I mean, I can guess, but I don't want to do that. But the other thing is multiple agents. See, what can happen is you can have multiple agents, either you like GAN kind of a thing where they are adversarial, or they can be cooperative. If they are cooperative, then they can, I mean, learn anything. And whether we could use two agents on different Markov solving a problem, I don't know. I mean, this is all the future.
The combining adversarial with RL will be interesting.
Yes, and I think it's a next logical step to do that, because you have multiple ways in which, and in this GAN, you have control over the environment. You have control over what you are. So I think that is.
Okay, any other questions? Friends on webinar, any questions?
Anything?
Okay, you can close out.
Okay, thanks a lot, everybody, and thanks for your patience and support. Let's see. Okay.